Okay, it's 8:05, and I think we can start.
Yes, go ahead, Ato. Happy New Year, everyone. Let's get started. Thanks.
All right, so today we will be going through the guest lecture for the course, and it's learning from text, a lecture by Alec Radford, who is kind of big name in NLP. He is one of the authors of GPT models, like one of the most famous architecture of recent years, and so he had contributed a lot over the years, and this lecture is focused on unsupervised learning of language, and more precisely on autoregressive language modeling. And today we will discuss the first half, which was mostly like a overview of NLP history and some important milestones on the path of NLP leading to today's results. Let's start with the motivation to use unsupervised language modeling and getting high quality supervised labels, dataset labels, is quite a tough task. It requires a lot of human labor, and therefore is kind of costly. On one hand, also it's often the case that to label the data sets, mechanical Turk service is used, and it's not quite the expert labeling, and therefore human labels may contain some artifacts which are undesirable. So the key takeout here is that getting a lot of high quality labeled data is hard and costly, and there exists a wide variety of NLP tasks. Therefore, we want to try and leverage vast amount of natural language data that is available for us through internet, so basically all the amount of information humanity has generated, like a substantial portion of it is available for us today through text. And if we can leverage this data efficiently, we can get hopefully really high quality language models. So there exists a number of methods for modeling language, and this lecture is focused on autoregressive language modeling, but there are other approaches, and some are more of historic interest, some are very influential as well. So for instance, there exists this word-to-vec approach, so we can model language as a set of word vectors. There is this CPC approach we discussed a couple of lectures before. which is contrast predictive coding. This is kind of general approach that can be applied to various sorts of data. There is BERT language learning objective, which is masked language modeling, which differs from autoregressive language models in a way that it allows to take into account bidirectional context, and that has proved to be useful for many downstream tasks in NLP. Also there is this approach by Electra authors, where the language model is trained as a discriminator in GAN setting rather than a generator. So the language model tries to classify if the word is correct or like a true part of the word sequence, or it's like a wrong word. And that has shown some good results in terms of compute versus the performance trade-off. But this lecture, we will mostly focus on the autoregressive language model. And yeah, as I mentioned, we have a lot of data which is present, and we can access it through internet, and essentially we can find like almost any kind of language data on internet. It was argued that like no one actually so it's hard to learn the common sense knowledge for these language models, because no one actually kind of encodes this common sense knowledge explicitly. But here is an example of how to open the door instruction. So yeah, so the internet is really big, and there is a lot you can find there. So what we want to do, we want to use this data to model language. And the most straightforward approach would be a co-occurrence-based approach. So we take, we build this very large vocabulary, we take all the words and count the co-occurrences of the words. And this co-occurrence count is likely to show us that kind of which words are likely to come together, and that would mean they are compatible in some way. So what can we do with that co-occurrence matrix? So here is an example from our paper by Clark, and it uses this pointwise mutual information solver to answer the questions. And here you can see that we have like 4 options to answer each question. So that random guessing would be around 25% accuracy, right? And this PMI solver produced 60% accuracy, which is not great, but okay, taking into account this is like a really simple brute force approach. We take basically we score all the options by this pointwise mutual information metric. We take the co-occurrences, so this P of xy would be probability of co-occurrence of 2 words, and then we normalize by the probability of the words, so that you know, some words are more frequent than others, so we want to normalize this, and then we take a logarithm. And in this way, we can kind of compute this combined co-occurrence for the questions with the answer words, and the highest score would be the correct answer, and that yields us 60% accuracy. So this kind of works, but there are a bunch of problems with this approach, and the most evident one would be we need to construct this matrix, which is kind of vocab size by vocab size matrix. And here is an example. If we take 1 million words by 1 million words, and for each entry we will use 4-byte integer, that would require 4 terabytes of storage. So that's a lot. And what we might want to do is to compress, to find some kind of compact representation for this matrix. And one of the approaches, and so that leads us to an approach which was really popular, like around, I think, up to like 7 or 5, 6 years before, and these are word vectors. So one of the famous word vector formulation is GLOW. So we take this matrix X, which contains word co-occurrences, and we are learning this word embeddings by optimizing this objective, which is kind of close to, we are like, if you look at it, we are trying, so if we drop this biases and this f of xi, then we would get, just we are trying to learn the factorized logarithm of this co-occurrence matrix. So we would try to factorize, but by adding these biases and also introducing this kind of weighting function, which depends on co-occurrence counts and is supposed to account for to compensate for the rarity of the words. So some words are really frequent and some are rare. So by adding these components, we get the objective to learn really nice word vectors. And but as you can see, we need to construct a full co-occurrence matrix to learn the word vector representations. And they used like 300 as the dimensionality of the vectors. There was another approach, this word2vec, and it was actually prior to GLOW. I think this was 2013, and it does not require the full co-occurrence matrix. What we do instead, we take the context. So here you can see that with it's shown with window size of 2. We take 2 words before and 2 words after the center words, and we are trying to just predict the central word here. And this is, you can think of it as a classification task, and by optimizing this metric, right, we can just use cross entropy to learn this, and by optimizing this metric we get word vectors. And another approach which yielded a slightly higher performance, I believe, was skipgram. So instead of predicting the central word, we take embedding for central word, and we are trying to predict the context. So that would make for each word in the corpus, we will have this four classification tasks. So we want to predict one word before and so on. And by making a context larger, we can get a better performance, but that would require more compute. So those were some of the word vector, most popular word vector approaches, and what this gives us. So here on the left, you can see the relative improvement by using glove vectors for initialization. And here's glove plus cow, which is like this cow is contextualized embedding, and we will get to it in a bit more detail later. And also, so this shows like we have a stable improvement over a wide variety of tasks when we initialize the model using the learned word vectors. And also we learn a bunch of useful relations. So the most famous, and I believe everyone have heard of it at some point, this like man to woman, skin to queen, and so on. So we can, what this shows that we can do vector operations on the word embeddings and find this meaningful relations, like it's shown here, like strong relates to strong, as clear relates to clearer, and so on. So a lot of useful information is captured by word vectors. So that's cool, but there is this problem that a language has a lot of structure in it, and the same word can have different meaning depending on the context. And here is an example where a word bank can have completely unrelated three interpretations depending on how it's used in a sentence. So it's but for word vectors we will have the same vector for bank for all of three. Like you can see, think of it as these are three different words that have the same representation, and it's obviously really hard to capture this kind of independent relations in a single vector, right? So yeah, and this leads us to this kind of conclusion or idea that learning just word vectors is kind of similar to learning only edge detectors in computer vision. So we have this like a feature extractor, but we do not model complex interactions between words. And for language, these interactions are rather important. So now let's think about how can we model language in more like integral way, right? And or synergic way. And here is like a history of language modeling in one slide, and we can go over important steps in this probabilistic language modeling. So the first one takes us back to the ideas from Shannon, from 1951, and this is like n-gram language models. So we take this local occurrences and try to model the next word based on the preceding words, so this number in gram would say how many preceding words do we take, the next step would be introduction of RNNs in 2018. And the RNN is a stateful model, which is supposed to compress the meaning of the context into a single hidden state. And then we can use this hidden state to predict the next word. And the next step would be, so if we have this hidden state, we want to first model both short and long-term dependencies, and we also want to be expressive enough to capture the longer context. And this would be like big LSTM models. So big would be for the expressivity, and LSTM is more kind of efficient modeling approach that allows us to capture both short and long-term dependencies. Next step would be transformers. So the transformer is a rather popular architecture right now, and it's a set architecture, but we can introduce some relative or absolute position embeddings, and that would model the next word. We can model it based on all context without any kind of compression using attention. We can attend to all the preceding tokens in a context. So again, next step would be a big transformer. So by scaling up, we can model much longer dependencies, and that essentially gets us to where we are now. So this, I think this is from GPT-2, and by it can generate like really nice, nicely sounding text. So that this it kind of makes sense of language and how to write. So that's kind of short overview, and now let's get a bit more detail. First of all, what is the kind of the most straightforward way to think about language modeling? We can think of it as having a bunch of strings containing like a bunch of, say, might be sentences, and then we can model it as a high-dimensional discrete data and fit a distribution model to it. So that is kind of very high-level view on the problem. So we want to get a probability of a string, and there was and still is some debate on the topic if it even makes sense. Not like if it even makes sense, but is it all what we need, or do we need something else to represent the language? You can see this quote by Chomsky from 1969, and he said that the probability of a sentence has like essentially no meaning, but right now we have a lot of successful applications of this probabilistic language models. So on the other hand, there's still a lot of debate if we need something more than just this continuous representations to model language. And but suppose we have this probability of a string, and what can we do with it? we can directly solve a bunch of interesting tasks. So, for example, a probability of grammatically correct string should be higher than probability of incorrect string, and but it probably shouldn't be 0 because there are typos. So the model should make some sense of the string, so it's not quite 0 probability. Also, this high quality probability model that we have here, it should capture the world knowledge. For example, the probability of sentence the hyena sets on the mat should be lower than the probability of the cat set on a mat. So that's something. And we also have, we can like do this inference given the prefix, say 2 + 2 = we can infer the next token, and should it be 4, and the most probable token should be 4, but there are also like 2 + 2 = 5. You know, there is a Radiohead song, and there is this like mathematical exercise to prove that 2 + 2 = 5. So the probability shouldn't be quite of 2 + 2 = 4 shouldn't be 1, but it should be high. And also, by having this probabilistic model of strings, we can do some like predictions. We can formulate a sentiment analysis as a conditional probability task, right? So we will have like this 5 classes, and we can infer which class is most likely by prompt construction. And there is even more applications. For example, for speech recognition, we can improve the speech recognition results by adding a language model to it, and we can resolve this ambiguity in the sound by comparing the probabilities of different transcripts. And the more probable transcript would be more likely. So we can correct the mistakes of speech to text like transcript by assessing the probabilities of different transcripts. And the same for translation model. We can kind of re-rank the translation by their probability. So the more common and more probable sentence would probably make a better translation. And in translation tasks, this essentially what usually happens is the language model is a part of the decoder, right? So that happens in end-to-end fashion. So yeah, there is a lot of applications for this probability of a string model. So let's proceed through the steps. How can we get this to this model? So first, we might want to do some preprocessing. For instance, it might be like some kind of language standardization. Here you can see that you might want to convert everything to lowercase. It's like an example of what can be done. Then we can filter out unfrequent words. Probably we will have some kind of limited vocabulary, and we want to include the most frequent words, but not all the words, because it would be infeasible. Then we want to tokenize and numericalize these words, and tokenization can be done in different ways. So we can do it on word level, we can do it on character level, and there are more like clever schemes for encoding the text to avoid these problems with unknown tokens. For example, there is like a byte pair encoding, which starts with separate characters and then combines them to build up a vocabulary. And there is another like this BERT style word piece tokenizer, which on the contrary like starts with long words and then splits them into tokens. So both approaches are used. I think the byte pair encoding is most popular now, but different approaches can have their benefits, and there is still some like it's a open research question. What is the best way to encode the text? Okay, so to proceed, we can make this very simple model by making this two rather simple assumptions. Uniform prior over tokens and assume all tokens are independent. Then we can assign a probability of 1 over vocab size to each token, and then compute the probability of a string as a product of the individual probabilities. But that would be not very good language model. So different tokens are more or less frequent, and we can model the probability of a token by their counts, like normalized counts, and that this will result in a unigram model. And next, we can model dependencies. So we can condition the probability of the previous token of the next token on the previous token, and that would obviously, given the first word, we have high kind of limited number of continuations we can use, and that would make a better model. So this leads to a bigram model, and we can generalize this idea by making like a prediction condition on a context. Also, there are some kind of there is possible problem here that, for example, we have some rare word like self-attention. Should it be 0? Probably not, because it would result in infinite loss. What was done instead? So people used some smoothing. So the model was so the probabilities of tokens were modeled like a mixture of a uniform prior with a unigram probabilities. So that something of some historic interest, but yeah, now we go to question: how do we evaluate these models? And there are two types of evaluation, and the evaluation of the first type is this kind of perplexity and bits per character, which so we evaluate directly how well do we compress the text. And yeah, so bits per character, it's just a number of bits you need to encode a single character of a sequence. And the perplexity is a logarithm of the cross entropy of the, or not a logarithm, the exponent of the cross entropy. So we have this negative log likelihood of a token, and then we can once we exponentiate it, we get the perplexity. And it is somewhat obscure. How do we even use these values? So they are not directly interpretable, and there are some estimates. So for human, the BPC would range between 0.6 to 1.3. So we kind of expect our model to be closer to the human performance. And just random guessing would have like log base 2 of 1/256, so that's 80 bits per character if we use this encoding. And
what's perplexity here?
So this was for bits per character, and then for perplexity, we can think of perplexity as like a branching factor of a language. So we have like when we generate a sequence of length n, we have like this space of perplexity power n, space of possible generations, and that would be a random guessing, right? If we assign probabilities uniformly and we pick across 10 equally likely next words, that would yield a perplexity of 10. So human level is between 5 and 10 from this BPC estimate. And for example, for translation, we have like much more constrained space. So the perplexity would be between 3 and 4. And essentially the perplexity, as you can see, it depends on how do we encode language, right? So for example, the perplexity for character level model and perplexity for word level model are not directly comparable. You need to convert from to relate this to quantities. And so I can share a link to a blog post which goes in a bit more details, but essentially the perplexity. So when you do language modeling, probably you are using as a cross entropy loss. And if you will take a natural logarithm of cross entropy, that would give you a perplexity of your model. That's like a more like mathematical view of it. So
it's an evaluation strategy that uses the space of the possible generations of a particular language model.
yeah, right.
Okay, cool.
Okay, so so this is kind of direct evaluation of language modeling, but it, as you can see, it's kind of might be tricky to interpret. And we have another way. This is like type 2 evaluation, where we would evaluate a language model by measuring its performance on downstream tasks. And for that, we can use like a lot of various metrics and here are some examples. Word error rate for speech recognition, blue is for translation, which this matrix kind of measures n-gram overlap over two language sequences, and there are various modifications to this matrix, but this is kind of appropriate for when you need to evaluate the similarity of two sequences. Then we have F1 score for part of speech tagging. We have accuracy for document classification. So all these metrics are relevant to how good our language model is. If it yields better downstream task performance, then it's kind of, we can conclude that it is a better language model. And as we will see in future, there is no strict correspondence between, for example, type 1 and type 2 results for some models. So yeah. With that, we can move on to overview of history of language modeling. So we will briefly mention some important milestones in the evolution of language modeling. So this first model by Benji et al. Is from 2003. 2003. So that back then, they were using a fully connected neural net with some skip connections, and you can see here we have this table lookup. Then we feed it to the MLP. We have tonnage, nonlinearity. We have some. And finally, we have this softmax over the vocabulary. So that is like the first straightforward approach to language modeling. The problem is we cannot take into account this sequential ordering of the words, and that was probably one of the early application of neural nets to language modeling. And the next important step was an application of recurrent neural networks to language modeling. So a language naturally has this sequential structure, and recurrent neural networks, what we do, we compress the context into some hidden state, and we are trying to represent a context as fixed size hidden state, and use it to predict the next element of a sequence. And this in this paper by Mikolov et al. From 2010, they showed good results in speech recognition by applying RNNs to sequence modeling. The next result was produced by using a character level RNN, and looking to this scheme here, you can see that it was quite complicated back then, but they got some nice results. So it learns a language, but it wasn't actually a lot better than n-gram models, and they used a very complicated scheme to optimization scheme here. They, I believe, used some second-order optimizers, and also they had this complex architecture where they had different set of weights for different characters. So that was a complex model, but that was a step towards like sequential language modeling. And then we get to this results from paper by Graves. He applied recurrent neural networks for generating language modeling, and he used the multi-layer RNN and LSTM as a building block. So LSTM is this kind of more complex model. If RNN simply has like a it can be thought of as a recurrent application of the same weights over and over. It has these problems with vanishing and exploding gradients. Also, it has some problems because we need to kind of compress the long context into a fixed size vector. So LSTM kind of alleviates these problems somewhat by having this modeling this more complex interactions. We have forget and input gates, which are where we compute basically the proportion of how do we want to mix the context and the new input, and it's computed based on the both this hidden two hidden state vectors and the new input. And yeah, so that's the same idea, but a bit more tricky. And there is also kind of gated recurrent units, which is a simplification of LSTM, like a bit more computationally efficient, but uses the same idea of gating the input and computing this state vector as a combination, a weighted combination of old state and the new state. So that was an important step which allowed like a high quality output like generation using neural networks. And the next idea is introduced in this skip sort vectors. And the idea here is to compress the meaning of a sequence into a single vector. So this time we are trying to learn not like a representation that is useful not to predict in only a single next word, but to predict the preceding and following sentences or sequences. And yeah, so here the idea is that we can embed this sequence of words rather than embed it incrementally. We want to embed it to be useful for a wider variety of tasks. And this resulted in kind of this nice clustering of learned representations. So that was somewhat successful. And the next paper from Dai and collaborators, again from 2015, they used, so they proposed fine-tuning the language model directly for downstream tasks. And so you can see this is quite early, and essentially that is what we use nowadays most often. But yeah, I haven't heard of this paper before. I thought this language model fine-tuning was proposed later by in ULM feed, but it turns out there was this idea appeared in this paper back to 2015. So yeah, that's interesting, but the reason it didn't overtake the NLP completely, it showed good results on classification tasks, but wasn't as successful on other tasks. But yeah, so that's essentially the idea of transfer learning as it was used in computer vision applied to NLP. So the next step was what would happen if we use more data and larger models, and there was an exploration of this in 2016 by Josefovich and collaborators, and they managed here, for example, to improve the perplexity from 41 to 23.7, basically by using more compute and more data. And so here you can see that they were using a very large vocabulary of 800,000 words, and therefore there was a need to use a sampled softmax to approximate the full softmax, because it's not feasible to compute like 800,000 kV softmax. All right, and so that's kind of scaling approach that was taken further and further by like we have a technological background to train larger models, and therefore we have access to more data. So that was like dominating the NLP research in the coming years. And yeah, so we have a lot of data, and it was shown that by using this a lot of data, we can improve results further and further. And to like once we have more data, we can feed larger models to this data and get even more benefit. So for instance, on the other hand, like by using state-of-the-art architectures of a small size with not enough data, we cannot produce high-quality outputs. And to be more precise, there was observed this power law scaling trend. So the validation loss here is shown to be log linearly correlated with the number of training data size, and also the same kind of correlation is observed with the number of parameters. And there was even more kind of sort of study of this phenomena applied to language modeling in this famous paper by OpenAI. They did a lot of research to scaling of autoregressive language model, particularly, and they found that this power law holds. So we can kind of gain the logarithmic improvement in the in matrix as compared to the number of parameters used of the model. And there is another, like a more recent paper from Google. It's called Scale Efficiently and something more. So you can find it here. It's relatively recent. And here authors researched the scaling on this encoder-decoder architecture. If you're familiar with T5 model, so they used that kind of architecture, and they compared how does it scales, and they compared the perplexity of the pre-training task. And you can see that there is this nice log linear trend here. But once we go to fine-tuning, it's not so obvious. So there is kind of a trend to have better performance as the number of parameters increases, but it's not this nice line as we observed here. And these different data points here are kind of compare different approaches to scaling the model. So we can introduce more parameters by making the model deeper, or we can introduce more parameters by making the model wider. And they found that this deep narrow architecture design works better, and also the scaling laws depend on the on this overall scale. So it will be different in different like parameter regimes, one can say. They also discovered that the standard T5 architecture, like T5 small and T5 large, were not, or T5 base and T5 large were not efficient on the Pareto trade-off curve. So that's another interesting paper on model scaling. So that can be interesting if you are developing these models, but let's move on to the next interesting observation. And this was in the paper by Alec Redford and collaborators. So they trained this LSTM language model, and on the large corpus of data, and they observed that there is a so-called sentiment neuron. So they carefully inspected the hidden state of the LSTM model, and they found that there is a particular neuron that models a sentiment. And this makes intuitive sense because if you can predict sentiment efficiently, then you probably that will be useful for predicting the next token, right? But this is a really interesting discovery, and it kind of shows us that we can discover attributes of the text in unsupervised fashion. So what's going on here? We just training a model with language model in objective, but we observe that it also learns to predict a sentiment. That's kind of interesting. And another research also done by Radford with this Gray guy, they tried to scale up the model. So the idea was to find out if the hidden state size is a bottleneck, and they use this block sparse weights and trained a model with over 18,000 units in the hidden state, and they verified that the performance is better as hidden state size gets larger. Yeah, so that's okay. So and another observation here in like this unsupervised discovery of the useful information. So his story close task, and the task is given some context. We need to predict the right ending, like to discriminate right ending versus wrong endings. And in this paper, it was shown that taking the pre-trained language model significantly improves the results on this task. And one can say that so by doing this simple like you can see here that we take the probability of the ending given a story divided by the probability of an ending, and by using this as a feature, we can improve the performance on this task. All right, and yeah, another idea which is also of historic significance is this mixture of expert idea. So again, the authors here are exploring the thought that maybe number of parameters is a bottleneck, and we need more parameters to model language more efficiently. So what can be done? We can learn information routing scheme and learn a different experts to kind of process the text depending on this context of the task, and not the context of the task, but depending on the properties of the text. And this allows to train very large models. For example, here it was possible to train a model with 137 billion parameters back in 2017, while keeping the compute like almost the same as for model having this only single expert, because the expert can be parallelized across devices. So if we are training model on multiple GPUs, we can arrange it in a way that the different experts are stored on different processing units, and the computation would be approximately the same as it is if we would have one expert. And so this mixture of expert approach was also used by Google for massively multilingual model, translation model, and they have shown that so the low resource languages can benefit from this by learning from the higher resource languages. That was another kind of interesting observation. And finally, we get to the turning point in NLP. So this was this paper by Peters and collaborators in 2018, which introduced deep contextualized word representation. So that's ELMO. And why it was so important, because they demonstrated, we could see that this idea of contextualized word representation, it was present in the COV vector embeddings, it was present in the DAI paper, but this one, they improved the results across 6 diverse tasks, and those were like a strong benchmark. But we can see that there was rather strong improvement over all of the tasks, different metrics. And the tasks were question answering, natural language inference, coreference resolution, name entity, so all kinds of NLP tasks, and the improvement was observed everywhere. And also it's shown that this improvement is even more significant in low data regime. So what have they done? They so we start here would be the word representation, which is not a contextualized. So here we like have a simple lookup table, but then we feed it to 2-layer bidirectional LSTM. And then we take the hidden representations from both layers, and then we compute a weighted mixture of the hidden states, both forward and backward representation, and that would produce a contextualized word representation. So that's the idea in ELMO paper. And after that, the contextualized word representations were kind of gone mainstream and were introduced to general public. So that was that had really big impact on NLP. And before that, people used this GloB or Word2Vec and trained the RNN on top of it from scratch. But now the contextualized words representation were used, but this approach still requires a specialized task-specific model. And so what we do, basically we train this language model to obtain contextualized representations. And after that, we freeze the bidirectional LSTM and just use it as a feature extractor again. So the next step, and it was kind of skipped in this presentation, but I guess it was also like important to mention, was this ULM feed, and essentially Ruder and Jeremy Howard used this kind of transfer learning, which was like highly adopted in computer vision at that time. They used it in NLP. So basically we train a language model, and then we just take the language model and fine tune it end to end for the downstream task. And they also got like state-of-the-art results on sentiment classification and yeah, and they are on the classification tasks. So the next important step was this GPT-1. So the transformer architecture came out. It was introduced for translation. So the first transformer paper was for using encoder-decoder architecture and was applied to translation. And Redford and collaborators, they use this transformer to with a trained transformer with autoregressive language modeling task, and then used that for wide variety of tasks. And as you can see here in the bottom part of a slide, that essentially we can use the same architecture for all the different tasks. So we have a classification. Basically, we just train a linear classifier on top of the transformer. For that, we can use the same architecture for NLI just by constructing a prompt in a way, like we have this start of stream tokens, and we have premise, then we have some delimiter tokens, and we have hypothesis, and then we have some kind of extract token, and then we again train a linear layer on top of that. We can do the same for kind of similarity. Again, we just take two texts, stack it together, feed it to transformer, then we can just swap the text and again stack it to transformer, and again we basically need just to switch those heads and use the same model for wide variety of tasks. And another interesting observation here was that this model, so it learns like a high quality language model. It can be used in this zero-shot setting, basically by constructing a prompt in a smart way. We can try to predict try to evaluate the task model on the task without any training examples. And so that was GPT-1. And you can see that it also shown an improvement on a bunch of tasks here. So that was another like important stage. And what OpenAI did, they took this approach further. There was GPT-2, and it was followed by GPT-3, and the difference between those models was mostly in scale. So they use essentially the same architecture with some minor engineering tweaks. And this GPT-3 model has shown interesting results in zero and few shot settings. So here we can see that. First, this plot shows how the zero and few shot performance scales with the model size. So along on the left plot here, along the x-axis we have the number of parameters, and on the y-axis we have score on superglue benchmark. And here you can see it does not achieve the state-of-the-art results, but in few shot setting, GPT-3 outperformed BERT large and fine-tuned for the task on the full labeled data set. And here this orange line, it only uses 32 labeled examples. So essentially, we do not need to train or fine-tune the model on the task. We just construct a prompt in a specific way to use this language model and capability of GPT-3 to do this few-shot inference. And even, as you can see, even a zero-shot inference performs much better than random guessing. So in this case, we don't have any labeled examples. We just construct a prompt in specific way and evaluate the model on it. And here is another plot that shows how a few shot performance scales with the number of examples. And this very large 175 billion parameter models with only 8 training examples, it performs on par with this like improved BERT++. So that's kind of retrained, I think, BERT here. But you can still see that there is a significant gap between state-of-the-art and few-shot performance. And in the lecture next week, we will speak of it a bit more. So there are more steps towards like few-shot or like zero-shot language model evaluation. And another interesting result, so basically GPT-3 is a very large language model, and its training corpus contains a lot of English, but also it has some French and German and Romanian, so it has all the different other languages in it. And yeah, so as it's trained on this diverse corpus of text, it observed a set of kind of translation pairs, and therefore here is like a few-shot translation. So basically, we construct a prompt showing the models that we want to evaluate it on, for example, French to English. And you can see that translation to English shown here in the right plot in solid lines. It performs better compared to English to other language. And that also makes sense because like GPT-3 is primarily English language model, so the best performance is on the English language. But as one can see here, that in some cases for English to other language, the GPT-3 few-shot model achieved state-of-the-art performance here. So you can see that for different languages like French to English, the previous state-of-the-art was 35 blue score, and they achieved 39. So that's quite impressive. And yeah, so even with zero-shot evaluation, it still makes some sense of what the translation should be. And zero shot would be just we'll construct some the prompt like, I don't know, some English and then a sentence and then German column, and the model is expected to produce a German translation of that sentence. And
that's where I had a question, Arto. So zero shot is with, you know, whatever the model is, and there is no pre-training, right? Meaning that you kind of immediately expect the model to perform. And few shot is you train, or pre-train, or do a little bit of example exposure. Then what is one shot? Is it just like with a single example?
No. In all cases, both zero shot and few shot, we don't have any training here. So the pre-trained model is evaluated. Maybe let me just quickly fetch a paper, and I will show you the I think it's best to see an example, and then it will be clear. I think they have some examples in that paper. So just a second.
Yeah.
Essentially, in zero-shot evaluation, we don't have any labeled examples at all. So that is we want to evaluate the model with like a zero train examples. So that's the idea. Now let me share my screen again. Okay, so now we need to think it here would be some examples of okay. So I just want to find some prompt examples here to demonstrate it. Probably that is in appendix. Or just let's check it here in the evaluation section. So here, for few-shot learning, we evaluate each example in the evaluation set by random drawing k examples from that task training set as conditioning, delimited by 1 or 2 new lines, depending on the task. So for example, say, let me just make up an example for you. So say we have a sentiment analysis task. So we have a sentence and a sentiment label. So we will construct a prompt in the following way. We have this movie was wonderful, positive. This movie was awful, negative. And then we have this movie was nice. And the model is supposed to generate positive or negative token, like a token that corresponds to a word positive or word negative after that. And that would be like few-shot learning with k equal to 2. So we do not do any fine tuning, but we use the labeled examples for prompt. And in this case, one-shot learning would be that we have only a single example of like what kind of label we expect to have, and then we want our model to kind of show the results. And for zero shot, we will not have any examples. So
sticking with the classification, so for one shot, for example, we could potentially have just a positive example of positive sentiment and then ask it to classify, but also classify negative sentiments, for example, correct?
Yeah. So, but the problem with this kind of zero shot evaluation is that model doesn't kind of know that it is supposed to generate particular token, right? But yeah, I guess it still shows some reasonable performance even with that. I will find more examples of prompt, and maybe I will post it just to not to take too much time, or maybe once we done with the lecture and we go to discussion, I will just search for that off screen.
Okay, sounds good. Thanks.
Yeah, so yeah, but I think we are done with this part of the lecture. And next week, we will switch to the transformer-based language model, and we will discuss the application of language models to the wider variety of tasks. So we will talk about BERT and its variants. If you'd like, we can just go over this slides introducing the transformer architecture. Those were skipped in the video lecture by Alec Radford, and I expect everyone here is more or less familiar with how transformers work. But if you'd like to just, we can just briefly go over it, or we can just proceed with discussion, and I will find this kind of examples for few shot and zero shot and so on. So
yeah, at least I'm familiar with the transformer. So unless anybody specifically wants us to go back and refresh, I'm fine with what you suggested.
Yeah, just let me know in the chat if you want to go and refresh and the attention mechanism, but I don't think it's necessary right now that the transformers are basically the most important, most popular architecture for all kinds of applications. So yeah, just kind of concluding comment here. It was quite interesting to see this historic perspective, and yeah, so this lecture is like about 2 years old, and it's fun to see how the ideas developed. And for example, this research direction by Alec Radford, how it proceeded from GPT-1 further to like GPT-3, and how just only by scaling the language model up, like a new with a theoretical question were raised, like how much these models understand the language at all. So.
Yeah, that was, I guess, it's a little more of the related to the second part of this lecture, but I haven't closely followed in the 2 years, but it seems that the only progress, I don't know whether only is the correct adjective, but the progress has just been in fine engineering details and scale rather than any kind of foundational advancement comparable in any way to transformers, or even, for example, to subsequent tweaks of the transformer like BERT or whatever, Roberta and the variants and stuff. But it's all been in that direction. And like you said, the only other thing I've seen more of is questions about, are these huge or gigantic language models really understanding language, or is it just that they are memorizing a whole lot of stuff and are therefore able to, spit out things that appear to be quote understanding, but their understanding quote unquote is limited.
Yeah.
So I don't know whether
essentially,
if you're tracking and what comments you have on that.
I think it's still like an open question if the model understands language and what understanding even means. So it, I think, it still lacks some common sense knowledge. For example, it might be, I think it might be a part and like an essential part of bigger system to get us to like artificial general intelligence, but by its own, it has its kind of limitations. For example, so this GPT 3 like engined dialogue showed that model doesn't have an idea of don't know in the answer. So when GPT-3 was like asked some questions that, for example, when the answer is not present in the text that it's supposed to answer about, it wouldn't say like, I don't know, or something like that. But still it will try to find the most generate most probable response from the text, based on the text. And so to filter out those answers, probably you would need some kind of heuristic on top of GPT-3, right? So that's like one of the limitation. Another, if we talk about this idea, how close are we to modeling something similar to human brain? I guess it's the human brain is still much more complex than very large transformer. Maybe it's possible that by just scaling up and making the tasks, pre-training task more difficult, like some kind of multimodal pre-training for like various kinds of inputs, like adding visual inputs to it, maybe some videos, audio and stuff, training that all together. Maybe it will result in some kind of general intelligence, but maybe not. Maybe it will require something completely different from neural networks. I'm not sure, and I don't think we are really close to answer still. So that's my opinion on it.
Yeah, my question was more even just in the language space. In the last 2 years since this lecture was delivered, has there been any kind of foundational or what one would think significant progress other than what you just stated of scale and engineering tweaks to what already exists?
All right, so yeah, mostly I guess this lecture does not cover, I'm not sure if it's covered T5. So, and all this kinds of encoder decoder architectures, and there has been some progress with those. So we will speak of it more in the next part of the lecture, but one interesting and idea was mixing the both like language modeling and downstream tasks, like more specific labeled data set at pre-training phase. So rather than doing like pre-training followed by fine-tuning, it was shown that by mixing a lot of tasks, one can get better performance. So it seems like there is some research space, and I will give you more details on it next week. But overall, I think we are in kind of incremental phase in NLP, and probably we will need something new to get to like another like jump, I guess. But yeah, that's something. I think there exists some research in like completely different kinds of language modeling. I was listening to a podcast with a man who's trying to apply some ideas from quantum computing to language modeling, and they're claiming that this kind of modeling everything in continuous space is not going to get us all the way, to human level understanding. But as you can see from this lecture, I guess this research to be noticed, it needs to deliver like a strong results at some like practical tasks. And yeah, I think both this hybrid systems and this new approaches are not quite there yet, like by not there to impress the general public and to go to gain more attention.
Yeah, and it seems like there is some opportunity, much like not Sebastian Ruder, but the guy who did the underlying multi-level LSTM model for ULM fit. I forget the guy's name now, but he had posited, and I think there is still some opportunity to try and generate models which are not as largely parameterized or gigantically parameterized as these models are, and try to achieve comparable even performance, or at least acceptable levels of performance, even if not beating the benchmark to the extent that GPT-2 or T3 or T5 do, but kind of do it in a parameter efficient way, if you will, rather than this way that these models can only be done or developed or by the Googles and the Facebooks, which have like enormous compute in their hands. And it seems it's an open question of whether you could come up with competitive models, but with a lot less parameter than these giant models.
Yeah, true. And the transformer architecture is not particularly specific to like language modeling or sequence modeling. It's a set architecture, and all the information about this sequential structure of the language, it's given by the position embeddings in transformer. And that was kind of it has both its merits and its like shortcomings. So we don't have like the number of like prior knowledge we introduce to here is minimal. So we basically feed a set of words, and the model learns to discover this structure. And on the other hand, we need more data and maybe more parameters to capture everything, because it's not designed to be efficient for this kind of tasks. There is also some research in applying graph neural networks to language, and like probably humans in our heads, we think of modeling the text as sequences, but a lot of like analysis in linguistics is done on these tree structures, and graph neural networks are efficient in modeling this tree-like interactions. So the structured interactions. Maybe there is some potential in that, but yeah, I'm not aware of any practical applications of graph neural networks in language, so I haven't seen where any use cases where people used like some kind of GNN instead of transformer. But yeah, definitely there is some potential. I can quickly now show the example to highlight this zero shot, one shot, and few shot. So here, let me. Okay, so here is just highlighting. So traditional fine tuning here is on the right side. We have a number of labeled pairs, and we do gradient updates based on these pairs. As you can see here, for any zero shot, one shot, and few shot, we don't have any gradient updates, but we use labeled examples to make a prompt. So the prompt consists of a task description. Here it can be like translate English to French. And then we have a prompt itself, like cheese, and we want to translate it to something, right? So in this case, it might be enough information for a model to produce the translation for the word cheese. But if we have a single, so the one-shot formulation would be translate English to French, then one example, and then the prompt for a word we want to translate. And finally, for few shot, we have a number of examples. And yeah, so for instance, here in zero shot settings, it's kind of harder for model to understand if we what is expected to come here after this arrow, right? But once we have some examples, the model may infer the expected output. So I hope that clarifies the.
Yeah, no, that's clear. Thanks. That helped.
All right, so
yeah, and Mayank also posted a blog post list, which I'll post as well.
Cool. So I think with that we can conclude today's part, and next week we will talk more about this applications of language modeling. Yeah, go on.
Yeah, I was just trying to add the applications with respect to transformers, as everything from 2018 we have completely shifted to transformers. So that's the only base, not the only, but majority, the majority of the cases of the large language models only use transformers nowadays. So yeah.
Yeah, but I think as Srinivas, I think you were talking about Stephen Merity research, and he's still working with
that's the guy's name.
Yep.
Yep.
Mm-hmm.
Yep.
recurrent neural nets, and also there is this SRU++ model. It has shown some good data efficiency, and essentially the transformers were not like considered better than RNN-like models for language, but it was just more like on the engineering side. They are much easier to scale up, to parallelize, and so on. So we can just train much larger transformers as compared to LSTMs. As you saw in that paper and on block sparse weights, it was quite tricky to train LSTM with this larger hidden state. But maybe we will find more ways to, use this sequential structure of a language in the future.
Yeah, there have been some approaches that are there, but they haven't been able to scale it up with respect to some graphs or some other models with some I think so that was with respect to some other type of hierarchical something. I'm not clearly remembering the exact details, but there was something hierarchical, some kind of a old model that they use, some kind of a old architecture that they used, but they weren't able to scale it up, which they thought would or kind of like replace transformers, but yeah, the progress wasn't there enough, and yeah, that's why multiple of the many approaches, I think so they have been kind of like shut down due to this scalability and latency issues that transformers are easily adept at solving with respect to the real world production use cases. So that's why I think so that's everything is converging towards transformers right now. I will post a link to the other type of approaches, some novel approaches that they tried. Yeah.
Cool, sounds great.
Cool. Thanks, Arto. We
Actually,
look forward to next week then.
I was gonna say, I see like a different division now, and I don't know what would be the way forward, but I see the difference between like a GPT-3 type of models, like a giant models where you can never fine tune. You can use it through APIs, or models that you can actually, fine tune possibly on multiple tasks. And I cannot tell like which ones are winning now. So.
Yeah, there is some work towards democratizing these giant models done, for example, by Eluter AI, and I think this big science project by Hugging Face and a lot of other institutions also interesting thing. So,
but yeah, so they may be usable, okay, and freely available, but then you still cannot fine tune them, right? So the usage there is different. Usage is still sort of prompt like or API like.
yeah, definitely. And also you need, for example, to run the inference, you cannot even run the inference without specialized hardware for that models, right? So you need to
so for example,
some of the
API.
cases, yeah.
Yeah, for example, we considered using GPT-J, but you actually need to host it, or find place where you can host it, and that's equally expensive as the GPT-3 almost. Anyway, thank you.
Yeah, that's why I think if somebody can come up with the opportunity is ripe for giving good enough, not maybe the level necessarily in all the tasks of GPT-3 level of performance, but good enough, but with much, much less parameters. At least the opportunity exists, although I don't know whether there is any, as Mayank was saying, there may not be many credible alternatives which have yet gotten to the point where the performance is acceptable for a lot of the tasks, but not at the same time not having these limitations that Yuri, you're pointing out of you can only use API or, because it's definitely the performance is very good, but it's out of the reach of most small entities. Forget about individuals, even small companies and stuff can't unless you just use the API kind of stuff. So there is that opportunity in that space, but I don't know that anybody has yet succeeded in breaking through to exploit that. Okay. Thanks, everyone. We'll meet again a week, and Nato will take us through the rest of the second part of this language model.
Thanks, everyone, for
lecture.
attending.
Thanks, everyone. Have a happy new year.
Thank you. Same to you. See you all next week.